for our first physics lab, we observed objects under constant velocity using the momentum principle and Newton's second law by making our own videos from home. For a object to be under constant velocity means that the net forces acting on the object have to be zero, or add up to zero by canceling each other out. Right here is the momentum principle, which is the change in momentum is equal to the net force times the change in time. And I have derived it down to the velocity form, where the final velocity is equal to the initial velocity plus the net force divided by mass times the change in time. For our purposes, the net force is zero, so all of this would be equal to zero, making the final velocity equal to the initial velocity, constant velocity. Right here is the position update, saying that the final position is equal to the initial position plus the velocity times the change in time. In my video, my friend rolled a baseball, and I tracked the velocity from the time a little bit after it left his hand to about halfway through the video. My axes would set right on the ball so that my baseball moved in the positive X direction, and it is about 40 frames long. The baseball would start at origin 0, 0, and if we play it, it tracks the points, and the entire segment is about 1.43 seconds long, with the final position being 1.261. Alright, so before we can enter it into the Python to get our desired graph, we must first know that the mass of the ball is 0.145 kilograms. And we know that the velocity is equal to the change in position divided by the change in time. So for us, our final position was 1.260 with our origin being 0, and it would be divided by 1.433 seconds to give us a velocity of 0.879972. And here it is right here in vector form. So if we go to Python, we see that we have our initial set, and the ball mass is 0.145, the initial position being the origin 0, 0, 0, and our ball velocity being our 0.879972. We're going to start at time 0, and right here, because our net force is 0, our final velocity is going to be equal to our initial velocity. So if we run this, alright, we see that the ball moves in the positive X direction, and on the graph right here it has a constant slope, giving it a constant velocity. This is the desired graph for the constant velocity problem for our baseball by entering it into Python. And for our actual video, right here the blue is what we made in Python, and the red is the information tracked from our video, and we can see that they are almost similar. The reason why the red might be a little bit off is because we assumed there were no forces at all acting on our ball, whereas the ball was interacting with the friction from the ground and a little bit of gravity. Alright, so our what if question is, what if we change the axes on which our simulation was run? And if we go back to Python, we see that in order to change the axes would be to change the way and the velocity. So we're going to make the velocity in this case, in this case we're going to make the velocity negative, and if we run it this time, we're going to see that it is the same graph in the negative slope, giving it the same constant velocity, but in this case we moved in the negative x direction instead of the positive x direction. And what does it mean? If we were to sum up the actual forces acting on a ball, if the net force was not equal to 0, this would mean that the velocity would not be constant. And to show this in Python, if we change this back to our original, would be to change the net forces acting on the ball. So right here, instead of having no net forces, if we made this 2 in the x direction and 2 in the y direction, alright, we would see that there is no longer a constant velocity, but instead there is an exponential growth in the velocity over the change in time. And that concludes our analysis of Lab 1, and hope you enjoyed. Thank you.
Now we're going to step through the same lab report and show you what the experts thought about it. Keep these critiques in mind when you start to plan your own video lab report.
Saying that the final position is equal to the initial position plus the velocity times the change in time.
A very good introduction. It's concise, and he makes it clear that he's using a constant velocity model. All the physics here is good.
In my video, my friend rolled a baseball with the final position being 1.261.
The presenter does a good job of describing his experimental setup. It's not really necessary to give the exact numerical values at the end position, but it is important to say which way your axes point and how you picked your origin.
To give us a velocity of 0.879972.
He should really be stating the right units, here meters and meters per second.
If we go to Python,
shooting a computer screen with a handheld camera doesn't normally give the best results, but here the text is large and in focus enough to read, so it's okay.
The initial position being the origin 0, 0, 0, and our ball velocity being our 0.879972. We're going to start at time 0.
He clearly describes how he determines the initial conditions of his computer model from his observations. This is a good model-observation connection.
The reason why the red might be a little bit off is because we assumed there were no forces at all acting on our ball, whereas the ball was interacting with the friction from the ground and a little bit of gravity.
This is something we like to see, a direct comparison of observational data with computer model results, an assessment of how well the model predicts the observed motion, and a physical explanation for the differences between the model and the observations. Nicely done. All
right, we would see that there is no longer a constant velocity, but instead there is an exponential growth in the velocity over the change in time.
Just as a note, this function is not actually exponential. We'll discuss the functional form of position versus time with constant net force later on in the course.
And that concludes our analysis of Lab 1, and hope you enjoyed. Thank you.
This video was presented adequately. It would have been better as a screencast, but the physics content was excellent. This was overall a very good video lab report.